Welcome to another session of the lesson. This lesson is again on the physics at A level. I'm Siamasaka, Korean Dance, presenting this lesson. So today again we're going to apply Newton's laws of motion on an object which is rigid, which is not moving, and then we'll apply the concepts of friction on the bodies. And so I hope this will cement the understanding of the physics concepts for bodies which are rigid, which are not moving, and the application of force of kinetic friction as well as static friction. But we'll particularly look at, since the body is not moving, force of static friction. And so here we go. So as I stated earlier, I said we are going to look at Newton's law of motion and how we can apply it to bodies which are not in motion. As you are aware, we did the concepts already under the laws of motion. And so today we are going to look at a solved question where we can apply it by looking at the concepts. And so the question is as follows. A book M has a mass of 50 kg. The coefficient of static friction between the book and the table is 0.3. The loop running from the book B to the knot at K is horizontal. Find the maximum weight of the book Z for which the system will be stationary. The angle between force T1 and force T2 is 160 degrees. And so this is the presentation of the question. We have a book here of mass M, and then there is a rope here tied to a knot where this is a rope, which is where there is tension 1, and then there is this other rope T2, which is tension 2. And then the angle between T1 and T2 is 160 degrees. So the knot here is K. And so we are told we are supposed to find the weight of Z. So Z is another book here which is hanging. And so these are very important questions which require us to apply concepts of static friction as well as resolving of vectors in two components. And so we need to pay particular attention because once we understand the concepts, that we can apply them to many other questions which are asked. And so if you look at these diagrams here, we can actually isolate the systems. This is actually one system, but however, if we want to deal with this question in a simpler way, we can isolate the systems. So we'd say we have a system, which is M here, another system here, which is from K here. And so, first of all, we deal with the system M. And so this book here has two forces, Fn, which is the normal force, and mg, which is the weight of this book. And then there is another force, since this tension, T1, is actually pulling to knot K. So there is friction as well, which is Fs, which is static friction. And so these are the forces which are at play on this system number 1. So this is a free body diagram. So I recommend that each time we have such questions, it becomes simpler for you to draw a free body diagram so that you can isolate the forces which are involved. So as I indicated earlier, we have a force T1 which is pulling this object towards the x axis, which is positive x axis, and then we have the counter force, which is the resisting force, which is the friction, which is Fs. Why Fs is because this is static, it's not moving. And then for a body which is not moving up or down, we note that the normal force, this is the force for which this table is pushing the book up, would be equal to the weight of the book. So we come to system number 2, which has a note at K. We note that T1 is a force now pulling to the negative direction. From here, it's pulling this way. Okay. And then we have T2, which makes with the horizontal. If we extend this horizontally, we will note that since this is 160, we can subtract from 180, and then it gives us 20 degrees. That is the angle it makes with the horizontal. And then we have another force here, which is Z, which is the weight of the book. And so once we have done this free body diagram, the question becomes very easy for us. So we are told that this body here is not moving at all. Okay. And so when you have such a equation, we should understand that the forces, the vertical forces, the sum of the vertical forces is supposed to be equal to 0. And the sum of horizontal forces as well, they're supposed to add up to 0. So you're supposed to add all the forces in the x-axis, and they should be equal to 0. And add also all the forces in the y-axis, they should also add up to 0. And so for the book on the table, we have already explained that the normal force is equal to mg. And the friction, which we saw here, which is opposing T1. As we are aware, static friction is equal to coefficient of static friction multiplied by the normal force. And the normal force is the same as mg, therefore to be equal to coefficient of static friction times mg. And we note that, as I indicated earlier on, that since this book is not moving, it means that the frictional force will be equal to the tension 1, because these are the only horizontal forces. So this force which is pulling it to the positive x-axis should be equal to the friction between the book and the table. And so you notice that T1 is equal to actually mu static, which is coefficient of static friction times mg. And so for the suspended book, which is this book here, we note that also if you look at the horizontal forces, we have this force here, which is T1, which is pulling to the negative side. And if you resolved T2 into component, this side which is adjacent would be T2 cos 20, T2 cos 20. So we note that here also this force T1 should be equal to, if this point should not be moving in the horizontal manner. So it means that T1 will be equal to T2 cos 20. So that's what it means here. We were saying for the suspended book, the horizontal forces T1 will be equal to T2 cos 20. For the vertical forces, we note that on the system number 2 here, on the vertical forces, we have the downward force, which is the weight of the book, which is Z, and the other one is the vertical force as a result of the component force for T2, which is T2 sine 20. And therefore, this is what we get. We get that Z is equal to T2 sine 20. And this is actually the concept. From here, all we are doing now is the mathematics, manipulation of the forces in order for us to get the value of Z. Otherwise, the most important concept here is actually identifying the horizontal forces, the vertical forces, as well as for this other part, system 1, to identify also the horizontal forces as well as the vertical forces. And so, as we indicated, we said mg which is T, actually mg times the coefficient of static friction, this one. Remember, we calculated it above. mg, which is equal to T1. And therefore, we can say, since here we said T1 is equal to T2 cos 20. So where there is T1 here, we can substitute it with the coefficient of static friction times mg. And this is exactly what we have done on this one. And we can make T the subject of the formula, and therefore we are going to get coefficient of static friction times mg over cos 20. And similarly, if we are to make T2 the subject of the formula from the vertical forces on system number 2, if you make T2 the subject of formula, you're going to get Z, which is the weight of the second book, divided by sine 20. And this is what has happened. And since this rope cannot extend, so we are saying that T2 is equal to T2, and therefore the tension is the same. Okay, so T2 is equal to T2, and therefore meaning that we can equate this equation here, we can equate to the other equation. When we equate it, this is what we get. It's merely rearranging. And thereafter, this same equation you can rearrange, you can bring sine 20 on top there, and the coefficient of static friction multiplied by mg, can bring it down here. We have merely rearranged this equation. And we know that sine 20 over cos 20 is equal to tan 20, according to trigonometric identities, which will be equal to the weight of the book Z over the coefficient of static friction multiplied by mg. And this is what we have explained here. And therefore, you can make now Z the subject of the formula. And to make Z the subject of formula, you merely multiply the coefficient of static friction times mg times tan 20. And then you substitute the values. Remember, from the equation, the coefficient of static friction was 0.3, and then the mass of the book was actually 50 kilograms, and multiplied by 9.8 newtons per kg times tan 20, which gives us 53.5 newtons. It means that we have found the value of Z. And so this concept we have learned here on the resolving of vectors into components as a result of isolating the systems is very important to learners. So it simplifies actually the way we can solve the equation. And so I hope the questions that we have gone through has helped us to upgrade the understanding of the concepts in static friction, as well as getting resulting forces in isolated systems. And therefore, I thank you. I hope we have enjoyed the lesson. And so next time, we'll make sure that we deal with another question which will help us to further understand static friction as well as the kinetic friction. And so I thank you very much. Remember to subscribe to my YouTube as you enjoy these free lessons. I thank you.